Good afternoon, dear students. So, how are you all? Fine.
I'm sure.
Okay. Milo.
I am not fine, sir.
Oh, Manas, why?
Again, I got cold and fever.
Oh, so any symptoms related to this COVID, Manas?
No, sir, I didn't get like that
Okay,
symptoms.
actually, the nowadays this weather is changing, no? So might be that thing may also happen, but be careful, okay? And take the this one precautions and have warm water. Okay,
Yes,
then
sir.
yeah. So we were discussing in the last class. We discussed two problems on the topic viscous damping, and I think all of you have seen that file I shared in the Google Classroom. Okay, so just go through it and practice it. Okay, otherwise see, you need to practice from the derivation. First you need to know how to analyze a system, then in the application part you need to practice some problem. Okay, then only you will find it easier. Otherwise, if you go to directly to the problem section, okay, so it will be difficult to you to understand, to solve the problems you will get difficulties. Okay, so from the basics, okay, from the Newton's second law of motion, from the free body diagram, if you just analyze the system, okay, and if you do the derivation, okay, in paper, okay, then only you will get the clear idea. Otherwise you will stuck, okay, or your formula will be wrong and all those things will happen. Okay, you will forget something. Okay, so some of the parts you will be missing. Okay, so that are the things that will going to happen. That is why you start from the basics. Okay, from the derivation you start for each and every topic. Okay, so today again we will be taking this damping section. So the next damping system which is basically used in the vibratory systems are this one, dry friction or Coulomb damping. Okay, so earlier in viscous damping there was a device. Okay, there was a apparatus. So that apparatus, it looks like a piston cylinder arrangement. Okay, it is basically a piston cylinder arrangement where there is a viscous fluid, okay, viscous oil. But here the name suggests that this is dry friction or Coulomb damping. So dry friction, so where it will happen? So in the various equipments, in the various machineries, in the various machine tools, so due to the rubbing, okay, due to the rubbing of the rough surfaces, so there will be change of frictional force. Okay, and due to the change of frictional force, there will be result in variations of coefficient of friction. Okay, with respect to the relative velocity. Okay, so due to that variations of coefficient of friction with respect to variations of velocity. Okay, because if two parts are moving, so there will be relative velocity. Okay, so due to that relative velocity, where there will be a difference of, there will be a change in the coefficient of friction, so there is a probability of producing the self-excited vibration. Okay, and that type of vibration is called as dry friction or Coulomb damping vibration. Okay, understood? So all of us know this basic expression of frictional force. So if two dry sliding surfaces are there where the normal reaction is R, then the frictional force in between these two mating surfaces, it is given by capital F, that is frictional force equals to mu into R. So here mu is the coefficient of friction and R is the normal force. Okay, so this coefficient of friction, if it is plotted against the relative velocity, okay, between these two mating surfaces, between the two sliding surfaces, for smooth surfaces, this coefficient of friction value, it gradually decreases, okay, for some instant, and when the velocity is increased further, so its value is constant. Okay, so from this plot, so you can elaborate this, okay, curve, okay, this one for smooth surfaces. And for rough surfaces, okay, and for for smooth surfaces it will be constant. For rough surfaces it will gradually decrease and it will be having one constant value. Okay, and for lubricating surface, lubricated surface, if in between the two matting surface or the sliding surface, if there is a thin layer of lubrication, then it will behave like the viscous damping. Okay, so the coefficient of friction will directly proportional to the increase in velocity. Okay, so this straight line, okay, at an angle of 45 degree, approximately 45 degrees, so you will get this kind of straight line. Okay, so this is the basic representation of this coefficient of friction with respect to this relative velocity. Okay, but here in our study, so we will basically concentrate on this curve where there will be dry friction. Okay, in between two rough surfaces. Okay, and the uh, coefficient of friction, basically it is constant. Okay, so we will assume that though it gradually first it decreases and then it is constant, but we will be considering that this mu is constant. Okay, for some extent, and if there is slight decrease in friction coefficient with increase in the velocity, then there will be a self-excited vibration. Okay, so here in this dry friction or coulomb damping, you should know the other name of this dry friction, that is also called as a coulomb damping. So two actually basic things we are interested in. Okay, so first one, as because this is the damping vibration, so first we will need to find out the frequency of damped oscillation. Okay, so in each of the type of vibration, so we found out the frequency of oscillation, frequency of motion. Okay, and the other thing, the rate of decay of these oscillations. Decay means what? So there will be some decrease in amplitude, okay, in each of the cycle, as because this is damped vibration, isn't it? So in damped vibration, so in each of the cycle the amplitude will go decreasing. Okay, and finally after some cycle, so the motion will comes to rest. Understood? Okay, so first we are going to find out the frequency. Okay, so to find out the frequency, so we will consider one system. So the basic system was the spring mass system. Okay, and here we will not show any external damper. Okay, because this is not a viscous damping where there is a piston cylinder arrangement. So here this damping is dry. Okay, so dry friction means this mass and the sliding surfaces will create the resistance. Okay, and this will behave as a dry friction damping. Okay, this will behave as a damper. Okay, this surface, rough surface. So here this mass is attached, okay, to a fixed end. Just wait. So you can see, so this is the equilibrium condition. Okay, so the mass is at rest initially. This is the equilibrium condition, and whatever direction, whatever parameter we will take to the right hand side of this equilibrium condition, we will be taking it as positive, and whatever parameters, okay, it may be displacement, it may be velocity, it may be acceleration, we will be taking on the left side of this equilibrium line, okay, which is imaginary. You need to think, okay, that it is acting vertically, okay, at the middle of this mass. Okay, so whatever be the parameters on the left hand side, it will be negative. Okay, because we will be going to use the Newton's second law of motion. Okay, so here all this thing it is written, but I have elaborated. Okay, so now what I will do, so I will displace the system, this mass, to the right hand side, because initially we need to give some initial velocity or initial displacement, isn't it? So what will happen? So the mass is displaced towards right. So this dotted line is the equilibrium line. So the mass is displaced towards right and moving towards right. Okay, because in this quarter cycle the mass is displaced towards right and moving towards right, but in the other next quarter cycle, okay, so what will happen? Though the mass was displaced to the right, the body was moving towards left. Okay, so we will consider the first quarter cycle when the mass is displaced. Okay, so mass is displaced towards right and moving towards right. Okay, so I think all of you are able to imagine this condition. Mass is displaced towards right and moving towards right. So in this condition, so how we can analyze the system? So when it is the system is moving towards right, the frictional force will act opposite to the direction of the motion of the body. Okay, so this is F, okay, which is acting, and it is shown by this arrow mark. Understood? Now we can apply the Newton's second law of motion. Okay, so for this system, so we will be applying the Newton's second law of motion for this system, B system. Okay, so mass is displaced towards right and moving towards right. So what are the forces? Those are acting on the system. So the first force which will be acting is an inertia force. Okay, so due to this motion of this mass, the inertia force will be mx double dot. Okay, so which will be equals to the summation of the external forces. So what are the external forces? One will be the spring force, which will be experienced by the spring, okay, against the direction of motion, because the spring is elongated. So spring force will act in the same direction as in the friction force. Okay, so the spring will try to regain its original shape. So that is why this kx will be acting in the negative direction, because in the assumption we have taken, then whatever parameters will be the left side will be taken as negative. Okay, so mx double dot equals to minus of kx for this drawing, and minus f, because the other external force is friction force. Okay, so minus f. Then if you just rearrange, what will happen? Mx double dot plus kx plus f will be equals to 0. So if you just rearrange this equation, you will get this type of equation: x double dot plus k by m into x plus f by k, because with f, as there is no term attached, so that is why if you want to take k by m common, then you need to divide f by k here. Okay, so will be equals to 0. This m will comes out from this x double dot term. So this will be the equation of motion. Okay, so when this equation of motion will valid when the system is displaced towards right and moving towards right. Understood? So now we will be taking this bracketed term x plus f by k will be equals to y. Okay, so this term will be taking it as y. So if you just take the double differentiation of x double dot, so this is constant, it will be 0, so y double dot will be there. So x double dot will be equals to y double dot. Okay, means d square x by dt square, it will be equals to d square y by dt square. Understood? So now you can write this equation of motion in terms of y. So in terms of y, what will be how this equation will become? So x double dot, I will be writing y double dot plus k by m instead of x plus f by k equals to, we will be writing y. Okay, so this will be 0. So now this equation is exactly the same equation as we got in case of the simple harmonic motion equation. Okay, when we were studying the undamped free vibration of a single degree freedom system, isn't it? So x double dot or y double dot plus equals to 0. So here the natural frequency of this system is what? K by m equals to omega n square, isn't it? So this under root k by m will become the natural frequency for this displaced system. Okay, for this vibratory system. Okay, so here this equation of motion, okay, or the body will oscillate with respect to this y equals to 0, means with respect to y equals to 0, the body will be having a simple harmonic motion. Understood? Because earlier x double dot plus k by m x equals to 0 is the equation of motion where the system was having a simple harmonic motion with respect to x equals to 0. Here the equation is in with respect to y, isn't it? So y means what? X plus f by k equals to 0. So with respect to this line, the system is having simple harmonic motion, and the natural frequency of this system is what? Omega n will be equals to under root k by m. Okay, so if you just want to describe this condition, okay, these two conditions, then you need to write that. So this is true. The system is having simple harmonic motion with respect to y equals to 0 only for that quarter of the cycle when the mass is displaced towards right and moving towards right. Okay, so this is the equation for 1 quarter cycle. Okay, means if there are 4 quarter cycle, then it will consisting one complete cycle. Okay, so this is the first quarter cycle, and for the first quarter cycle the body will be in simple harmonic motion with respect to this line. X plus f by k will equals to 0. With respect to this line, the body will be in simple harmonic motion. Okay, and the natural frequency is this one. Now there is another quarter cycle, isn't it? So the body is displaced towards right and moving towards right. The body is displaced towards right and moving towards left, because after reaching the maximum amplitude, so it will try to move to the left hand side, isn't it? So for this condition, so we'll be analyzing again the system. Okay, so in this condition, the frictional force will act in the opposite direction of the motion. Okay. Now if you just see the external forces, as because the spring is so the spring was stretched, so the spring force is acting in this direction, and frictional force, as because it is displaced in the right hand side but moving towards left hand side, it is having this much, okay, frictional force in the right side, means positive direction. Understood? So if you just apply Newton's second law of motion, then you will get mx double dot will be equals to minus kx minus f. Okay, minus kx, minus kx plus f. Why? Because this is to the right hand side. Okay, this f is having now positive value. Okay, so minus kx plus f. So if you just rearrange, so what you will get? X double dot plus k by m. So x minus f by k will be equals to 0. So again we will be taking this bracketed term as y. Okay, so earlier it was x plus f by k and we have taken it as y. Now we will be taking x minus f by k will be equals to y. So if you just double differentiate this x, then you will get for this x, it will be x double dot, and minus f by k it will be 0 because it is constant, equals to d square y by dt square. So y double dot. So x double dot will be equals to y double dot. Okay, and substituting this value of y double dot in this equation, we will get y double dot plus k by m, and instead of x minus f by k, we will be writing y will be equals to 0. Understood? So with respect to this y equals to 0, so the system is now in simple harmonic motion. Okay, but here y is what? X minus f by k. Understood? So with respect to this line, now the body is under simple harmonic motion. Earlier, when the body was displaced towards right and moving towards right, the body was in simple harmonic motion with respect to x plus f by k equals to 0 line. Okay, now in this condition, when the body is displaced towards right but moving towards left, okay, means in the next quarter cycle, the body is in simple harmonic motion with respect to the line x minus f upon k equals to 0. Understood? So in both the cases, you will get the natural frequency as under root k by m. Understood? So the same natural frequency we will get in each of the quarter cycle, means the system is having a natural frequency of under root k by m. So it is directly observed from the derivation. Okay, so similarly there will be other two cycles when the body is displaced towards left and moving towards left, okay, the third quarter cycle. And when the body is displaced towards left and moving towards right, the fourth quarter cycle. So in each of the cycle, so the natural frequency of the system will be under root k by m, and we will see that the body will be in third quarter cycle, the body will be in simple harmonic motion with respect to x minus f upon k equals to 0, similar to the second cycle, okay, second quarter cycle. And in the fourth quarter cycle, the body will be under simple harmonic motion with respect to x plus f upon k equals to 0. Okay, so here again I am not doing that derivation, but from here it is clearly you can see that if in this direction, in the first quarter cycle, if the body is in simple harmonic motion with respect to x plus f by k equals to 0, so in the fourth quarter cycle also it will be in the simple harmonic motion with respect to the same line. Okay, so the first quarter cycle and the fourth quarter cycle are in simple harmonic motion with respect to x plus f upon k equals to 0, and in second and in third quarter cycle the body is in simple harmonic motion with respect to x minus f upon k equals to 0. Understood? So that the all thing, okay, all the quarter cycles can be represented by this drawing. Okay, so this is our initial equilibrium line. Okay, initial equilibrium line, the dotted line which I showed in the figure. So the body starts vibrating from this line, okay, from this point. So this will be the locus. So you will see that there will be a decrement of amplitude. Earlier the amplitude was this much from here to here. Now this amplitude in the next cycle is this much. Okay, so some amplitude it is getting reduced. Are you getting? So some amplitude it is getting reduced in each of the cycle because this is damped oscillation, and finally it will vanish, okay, after some cycles or after some time, because this is t. So x with respect to t, amplitude with respect to time. So this is called as displacement time plot of a system having free vibration with coulomb damping or dry friction damping. So from here omega n equals to under root k by m, so we can find out the time period, okay, or time period to complete one cycle. So it will be 2 pi upon omega n, isn't it? And as because this is one complete cycle from a to e, this is one complete cycle, so time period is how much? 2 pi upon omega n, isn't it? 2 pi upon omega n. So each of this quarter cycle can be divided into 4 equal halves, isn't it? So 4 equal halves if you divide, so each half each part will be equals to pi by 2 omega n, pi by 2 omega n for this time period. Okay, so for this quarter cycle, okay, so this is the time taken to complete that quarter cycle. This is the third quarter cycle time, this is the fourth quarter cycle time. If you just add up all these 4 quarter cycle time, so you will get the time period. Okay, so you will get this one, 2 pi upon omega n. Understood? Now if you want to just draw the line with respect to which the first cycle and the first quarter cycle and the last quarter cycle is simple harmonic motion, so the first line will be x plus f by k. So x plus f by k means what? X equals to 0 means y line, isn't it? Y axis, and here x plus f by k. Okay, so this is the line x plus f by k. So this is x, this is displacement axis, and this x is also the displacement one. Okay, so this is x plus f by k line, and this is x minus f by k line. Wherever there will be decrement with x, so it will be just upside of this line, mean line, because this is x equals to 0 line, isn't it? The mean or equilibrium line. And here this is x plus f upon k. Understood? So here you can see from A to C, the half cycle is simple harmonic motion with respect to the line x minus f upon k. Okay, means this is the second quarter cycle and the third quarter cycle actually. So if you just start from here, So this will be the first quarter cycle, but this is the second quarter cycle and this is the third quarter cycle. That is why this is x minus f upon k equals to 0. And next quarter cycles, this is fourth and first. Okay, so those are simple harmonic motion with respect to x plus f upon k, which I have already elaborated. Okay, so our first task, it is completed. Means in this dry friction or Coulomb damping, so our first interest is to find out the natural frequency or frequency of damped oscillation. Understood? So we have found out the frequency of each of the quarter cycle, and finally we have seen the graphical representation, okay, of the time displacement graph. Okay, and we have seen that in each of the cycle the amplitude, it is decreased a little. Okay, and in the next task we are going to see what is the by what amount the amplitude it is decreased actually. See, from x equals to 0, this is the amplitude, and from x equals to 0, this much is the amplitude. So by this much length the amplitude is reduced, and it is given as 4f upon k. But how this will be 4f upon k? Okay, so we are going to find out. Understood? So for this, actually I will suggest not to go by derivation, go by this derivation. So we will take another derivation, okay, or another analysis, because here in this book Grover, from where I have taken this material, okay, so there are few points which are missing in the diagram. Okay, so if you just go through this line, so you will be puzzled. Okay, you will be confused. So that is why just ignore this derivation. So we will go by another derivation. Yeah, so this derivation is taken or analysis is taken from another book. Okay, so here it is actually shown in a very simple way. You will also get it very easy actually, and you won't forget. Okay, because already you have studied so many things about this Newton's second law of motion, how to apply this concept on the free body diagram of vibratory systems. Okay, so you can see if the body is displaced towards right, the frictional force will be acting in the negative direction. So this will be the equation of motion. Okay, so this will be the equation of motion after applying Newton's second law of motion. And when the mass is moving to the left, so this will be the equation of motion. Okay, so we will be taking any of this equation and we will be solving, and finally we will get by how much amount the amplitude is decreased in each of the cycle, okay, of this damped vibration under Coulomb damping. So let's take this equation, mx double dot plus kx minus f equals to 0. So for this equation, differential equation, the solution basically it is given by this way. Okay, so b cos omega nt plus d sine omega nt plus f upon k. As because this is a vibratory signal, that is why this cos and sine terms it is there. So in simple form, this equation it is taken. Okay, already we have seen the solution of this type of differential equation, where solution is given by c1 cos omega nt plus c2 sine omega nt. Okay, as because there is a term on the right hand side, earlier it was 0, now it is having some value, frictional force, that is why it is written as f upon k. Understood? Okay, so for this equation or for this solution, so what we will be doing, so we will be putting the boundary condition in the solution. Okay, so first we will differentiate this x with respect to t, then we will get the velocity. So okay, you can also practice this thing, but here it is directly shown. Okay, so we will differentiate it once, and then we will be putting this boundary condition. Already we have got this boundary condition, x equals to x naught when t equals to 0, x dot equals to 0 when t equals to 0. Means initially there was a initial displacement. Okay, and initially there was no velocity, no initial velocity was there. Okay, so if you just put these two conditions separately in displacement equation and in velocity equation, so what you will get b value as x naught minus f upon k. Okay, so we in terms of x you will put x naught, and in terms of this one t you will put 0. So this term will become 1, this will vanish. So b plus f upon k will be equals to x naught. Okay, so b value will be x naught minus f upon k, and if you put the value of this x not equals to 0, t equals to 0, okay, then you will get d value will be equals to 0. Understood? So now we will be putting these two value where, so we'll be putting these two value so in this equation. Okay, so if you put d equals to 0, so this term will vanish, so only this term will be there, b cos omega n t plus f upon k. So instead of b, we will be writing x naught minus f by k cos under root k by mt plus f by k. Okay, so this is the solution for what? Or 1/2 cycle. Okay, so this is the representation of displacement. Understood? So if you want to, yes, this is the equation of motion for the displaced system. So if you want to find out the displacement, means this is x means what? This is the vertical amplitude, isn't it? This is the vertical amplitude, because already we have seen here in this drawing. This is the vertical amplitude. Okay, this is the amplitude. For this diagram, it is vertical. Okay, so this is nothing but the amplitude. Okay, expression of amplitude. So for 1/2 cycle, if you want to calculate the amplitude, so how you will going to calculate the amplitude for 1/2 cycle? So when t equals to pi by omega n. Okay, so pi by 2 omega n is the time taken to complete 1/4 cycle, as we have seen in the last drawing, pi by 2 omega n. So pi by 2 omega n, so this will comprise to half cycle, and this is another half cycle. So if you just add these two, okay, first two time, then you will get pi by omega n. Okay, means for completing half cycle, so time needed, it is pi by omega n. Okay, so if you just put in this equation pi by omega n instead of this t, okay, so pi by omega n, so omega n is what? Under root k by m. So k by m, under root k by m, under root k by m, it will be cancelled out, only pi term will be there, and plus f upon k. So cos pi is what? It is -1, so minus of x naught minus f upon k plus f upon k. So if you just calculate, then you will get minus of x naught minus 2f upon k. Okay, so earlier, so what it suggests actually, so earlier, initially, from x equals to 0 line, x naught was the amplitude. From here to here, it was the amplitude. Now, for this damped oscillation, as because this is the equation of motion, so in 1/2 cycle, the amplitude, it is reduced by how much? 2f upon k. So in 1/2, the amplitude reduction is 2f upon k. So in one single cycle, so twice the reduction will happen, isn't it? Because in 1/2 of a cycle, the reduction in amplitude is 2f upon k. So in the another half, there will be again a reduction of 2f upon k, which we can show, and the total reduction, it will be 4f upon k. Okay, so here, from here to here, this is one complete cycle. Okay, and the reduction in amplitude, okay, it is vertical amplitude, means in this representation, it is shown vertically. Okay, so the reduction in each of this amplitude, it is 4f upon k. In the next cycle also, there will be a reduction of 4f upon k, decrement. In the next cycle, there will be again reduction of 4f upon k. Okay, so if a particle or if a system, okay, comes to rest under damping, which is under damping condition, if it comes to rest after 3 cycles, then what will be the decrement of amplitude? If you are asked, then you need to say that it will be 3 into 4f upon k, because after 3 cycle, it is having 0 velocity, or it is under a static equilibrium condition, or it is in static condition. Then you need to say that after 3 into 4f upon k, okay, times this decrement of amplitude, the body comes to rest. Understood? So in one cycle, it is 4f upon k. In 2 cycles, it is 2 multiplied by 4f upon k. So just like it will decrease. Understood? So this is the actually analysis which is needed for this dry friction or Coulomb damping. So 2 things we have studied. One is the calculation of frequency in this dry friction or Coulomb damping, and second one is the decay of the amplitude, the rate of decay of the amplitude or the oscillation in each of the cycle. Okay, for which type of vibration? For coulomb or dry friction vibration. Okay, so I think all of you have got the idea what is dry friction or coulomb damping. Okay, I will be sharing this PDF file in the Google Classroom, as well as I will upload this video in this Google Classroom. So if you have any doubt, you can ask me, or after watching this video also, or watching this lecture also, you can ask. Okay, but you need to complete these topics very soon. Okay, because your class test is near at hand, and up to this today's class your syllabus will be there for, okay, for this class test too. So if you have any doubt, you can ask, and if there is no doubt, you can leave this meeting. Thank you.